Okay, so in the last class we had stopped till AC circuits containing only inductors. So phasors we had seen yesterday. Phasors were rotating vectors, and their depiction graphically through a diagram was known as phasor diagram, which represented the differences between alternating current and voltages. Then we had started with AC circuit containing only resistor. So this type of circuit, this is known as what? This is known as purely resistive circuit. I is equal to I naught sine omega t, E is equal to E naught sine omega t. This we had seen, which showed that both are in the same phase. And then we have AC circuits containing only resistors, only inductor. Derivation we had seen, which showed us what? That current lags by 90 degree and EMF leads by 90 degree. One more quantity, the resistance that was obtained in case of AC circuits having only inductor was XL. XL was what? XL was simply inductive reactance, which we see. And this was a phasor diagram to depict what is the relation between the current and voltage and which quantity is ahead of which quantity. So voltage is ahead of current by 90 degree. Now we are left with the last type of circuits among these, that is the AC circuits containing only a capacitor. So same thing, the way we have been doing, capacitor will be connected like this, and E will be equal to E naught sine omega t. So this is the potential voltage, which you can say, which is equal to E naught sine omega t. There's a relation between voltage, charge, and capacitance in the formula of capacitance. Can anybody tell me a formula that connects both all these threes? All the three quantities: voltage, current, voltage, charge, and capacitance. Formula of capacitance only, if you say, that will be included. Anyone? No, not C by V. See, Q is equal to CV is the formula of charge, and capacitance is equal to charge divided by potential. This is from your chapter 2. So here also, if you write the value of potential, potential will be equal to what? Q by C. This will be equal to potential. All these three formula will be used. So Q is equal to CV. This is also one of the formula. So put the values of V, that is EMF. So Q will be equal to what? C epsilon naught sine omega t. This is what? This is your charge. Now, if I have to find out current, how do we find current with the help of charge? If charge is given, how do we calculate current?
Q is equal to I by T.
Q is equal to I by T. See, I is equal to Q by T. dq over dt you have no for charge. See, charge is present, some amount of charge will be present. Now, amount of charge that changes with respect to time, that is known as current. So here also charge is equal to C epsilon naught sine omega t. So if you know the value of charge, if you change the rate of change of charge gives you current. So here current will be what? dq over dt. It means you have to differentiate C epsilon naught sine omega t over dt like this. So see, here omega will come out, it's a constant. C epsilon naught, this is already constant, and this is cos omega t. So I is equal to, you can write it as omega C epsilon naught sine omega t. This can be written as omega C E naught cos omega t. Simply, this can be written as omega t. Now, one more thing. If we want to write it in terms of sine, this is in terms of cos. If I want to write it in terms of sine, simply by using the identity omega C E naught, this becomes sine pi by 2 plus omega t, or theta plus 90. Even if you want, you can shift it and write it as theta plus 90. Now see, if I write omega C E naught by, if I write it as 1 by omega C, check whether there will be any difference or not. If I am writing E naught divided by 1 by omega c. See this term that is in the denominator, it will go up and it will become omega c E naught. So there is no difference if I write omega c E naught as E naught divided by 1 by omega c. There is no difference that is obtained over here. So E naught divided by 1 by omega c, this is equal to, this can be written as, this both are same C class. If I write E naught divided by omega c, this is different. This is E naught divided by omega c. But even if I write this also again in the denominator, 1 by omega c, then this omega c goes up in the numerator and this becomes omega c E naught. So that's why I'm writing this term as 1 by omega c only. And here it is left sine omega t plus pi by 2. This is the value of current. See, E naught divided by 1 by omega c. We'll discuss it, what is E naught by 1 by omega c. But for the time being, let's say this is the maximum value of current, peak value of current that is obtained. So I naught sine omega t plus pi by 2. Now, main thing that you have to note over here, this is the equation of current. EMF's value was E naught sine omega t. Current's value is I naught sine omega t plus pi by 2. Is there any phase difference or not? Or do you think both are again in the same phase like the case of resistors?
Ma'am, there is phase difference.
Phase difference, how much, Anushka? What is the angle?
Pi by 2.
Pi by 2. And can anyone tell me, is current leading or EMF leading right now?
Current leads voltage by the phase difference pi by 2.
Perfect. Current leads the voltage. See, when we had seen the equations of current and resistors, both were having I naught sine omega t, E naught sine omega t. So we could easily conclude both are again in the same phase, right? When we had seen the case of circuits containing only inductor, that time EMF was E naught sine omega t. But I was what? I was I naught sine omega t minus pi by 2. Minus pi by 2 means it was lagging by 90 degree. If EMF is here, it will be lagging by 90 degree. Now what we have? We have E naught sine pi by E is equal to E naught sine omega t for the circuits having only capacitor. But now we are having I as I naught sine omega t plus pi by 2. It means plus means what? Additional. Addition is there, so it means additional, means it is ahead of EMF by the angle pi by 2. So if it was lagging behind, now it is leading the value of EMF. So this is one important thing that you have to remember among all these. And also, this is definitely for sure that current will lead here. And C class, please make these things clear in your mind, which quantity is leading which quantity, because at the end this is only that will be helpful. Today only we'll after this start with LCR circuits, then you will note how all the three will get combined. Okay, so current leads voltage by 90 simply. Now the question I naught, I had written I naught as E naught divided by 1 by omega c. So again, this is similar to I is equal to V by R. Current is equal to potential divided by resistance, according to Ohm's law that we have studied. Now C class, it means if this is EMF, definitely this has to be the resistance. So this term, this time the resistance is written as what? Written as XC. And now this is known as capacitive reactance. Now what's the difference? In case of a circuit that is having only a resistor, the work of resistance or the work of opposition, that is done by what quantity? That is simply done by a resistor. Resistor opposes the flow of current, opposes the motion of current, right? So that work is done by resistors. So, the circuits having only resistor, opposition to the flow of the alternating current. When the circuits having only inductor comes, that work is done by XL. XL is what? Inductive reactance. It opposes the flow of alternating current within the circuit. Fine. Then you have current circuits having only capacitor. Here you have XC. So XC or capacitive reactance means the resistance work or the opposition work to the flow of motion of alternating current. This is done by XC. Now see, these circuits are different from your DC circuits, as I've told you in the last class only, that AC circuits are completely different. Your direct current or the normal circuits for that we have for these electric bulbs and tube lights and all, that is a different circuit. That is your direct current that comes. Fine. It has a resistance that opposes the flow of direct current. Direct current means in the complete entire circuit, one type of current is only flown. If, for example, in the entire circuit, if I say 2 ampere of current is the equivalent current, so 2 ampere of current will be in certain segment of wire. For example, this is a segment of wire. From here to here, if this is one wire, 2 amperes of current is flowing. So if you choose any of the points, 2 amperes of current will only flow. So that opposition is done by a resistor. Resistance circuit, equivalent circuits have also been drawn. But for alternating current, you have resistance, you have inductance, and you have inductive reactance and capacitive reactance. So XC can be written as 1 by omega C. XL was what? Anybody who remembers this? XL, yesterday we had seen.
Omega L.
Omega L, yes. So Ahmed is right, this is omega L. I want to ask you one thing. Is your first name Ahmed only, no? Or you refer yourself as Usman?
This one, Ahmed.
Ahmed Usman, no? So XL is omega L. Now XC is not omega C. Many students get confused whether they write XL as omega L, but when it comes to XC, they write XC also as omega C. Now that will make your answer completely different, because XC will come as a separate question as well. And 1 by omega. Omega also we know omega is written as 2 pi nu. So you can write omega as 1 by 2 pi nu C. And C is what over here that I'm writing? C is the capacitance, value of capacitance in a circuit. Capacitance we have studied. Capacitance is what? The SI unit of capacitance is farad. That capacitance only. 3 microfarad, 4 farads, all these things. So XC is 1 by 2 pi nu C. Now see, class. 1 by omega C XC, capacitive reactance, opposition offered by the capacitor to the flow of AC through the circuit. Now it is 1 by XC was equal to 1 by 2 pi nu C, whereas XL was equal to 2 pi nu L. See a difference. XC is inversely proportional to frequency, whereas XL, we have already plotted the graph as well. This is directly proportional to frequency. So if you plot a graph between XC and frequency, this time you will not obtain a straight line. It will be a, because XC is inversely proportional to the frequency. XC becomes inversely proportional to the frequency. So questions also come. If the paper is easy, then only definitely this type of question will come. XC, differences between XC and XL. So you'll have to say, first point will be that it is the resistance opposed in which circuit. Types of circuit you will mention, circuits having AC circuits having only capacitor, AC circuits having only inductor. This becomes the first point of difference. Then you'll have to mention about the relation between the XCs and the XLs with the frequencies, linear frequencies. Fine. All these things like this only you have to mention. So these 2 points will be there. Then formula you have to mention. Units will be the same because units are for resistance only. So resistance SI unit, you know, the SI unit of resistance is what? SI unit of resistance is. So SI unit of resistance is ohm. So XC and XL both have the same SI unit, that is ohm. So there will not be any change within the SI units of these. Now, if you plot the phasor diagram and the graph, see this time current is ahead. So EMF, let's say EMF is this. This is EMF. If I am plotting the graph, current when EMF is zero, when EMF is at the origin, EMF is zero. Current has already covered 90 degrees. Pi by 2 path has already been covered by the current. So current's path will be like this time. Earlier it was EMF that was covering this path. Now this is current that will be covering this path because this is 90 degree ahead of EMF. See, it has already covered 90 degree path when EMF has just begun its motion. And when current will complete one, it will become back to zero. EMF will then be 90 degree because there is a phase difference between them. And same thing is better if you see with the help of this phasor diagrams. For example, let's take the EMF is somewhere here. This is EMF. So when we had the circuits having only resistor, see, I'm repeating all the three circuits together. It was overlapping. Fine. When we had circuits having only inductor, current was somewhere here behind. Now we have circuits having only capacitor, so it will be leading it. So now current is leading voltage by the phase difference pi by 2 or 90 degrees. So one conclusion that I've already written, you don't need to write down. Before that, C class, IRMS is equal to I naught by R. So in case of circuits inductor having inductor, you can write it as I naught by root 2. See, this is what? This is simply, this is telling you, this line is telling you, IRMS is written as I naught by root 2. Fine. IRMS can be written as ERMS divided by resistance, right? Current RMS can be written as voltage RMS divided by resistance using Ohm's law. So resistance value you can change according to the circuit. If your circuit you are able to see that this is a circuit having only inductor. So you can write IRMS is equal to VRMS divided by XL. For peak value, you can write I naught is equal to E naught divided by XL. Like this, you can write down. So that modification you can easily do just by replacing the resistors. That the questions also we'll do. Before the questions, a small conclusion. Then we'll come to the questions. For circuits having only resistor, E was equal to E naught sine omega t. Current is equal to I naught sine omega t. EMF and current both are in the same phase. So formula of current will become I naught will be equal to E naught by R and IRMS will be equal to ERMS divided by R. Fine. This is clear. Circuits having only resistor. Now coming to circuits having only inductor. E was equal to E naught sine omega t. I is equal to I naught sine omega t minus pi by 2. So minus pi by 2 shows what? That current lags or voltage leads with a phase difference of 90 degrees. So you had the constant I naught is equal to E naught by XL you can use, E naught by omega L, E naught by 2 pi nu L, all you can write. And similarly for IRMS, you can write ERMS divided by XL. Then coming to the last circuits that we have done just now, circuits having only capacitor, E is equal to E naught sine omega t, I is equal to I naught sine omega t plus pi by 2. So plus pi by 2 shows current leads, whereas voltage lags. Again, phase difference will be 90 degree. So I is naught is equal to E naught by XC. XC we have studied right now, which is 1 by omega C. And ERMS can be written as IRMS. See, IRMS can be written as ERMS divided by X. So no need to copy these 3 points. Till above you can copy it down. These 3 points are just for revision. So anybody who wants to write it separately, you can note it because I have written in a very haphazard manner. Fine. Any doubts till these circuits? Because now we'll combine all these three. So before that, tell me, any queries till now? Clear?
Yes, ma'am, clear.
Okay, good. Then note down the circuits having only capacitor. Then we'll do some numericals, because numericals we have not done from this topic. Circuits having only capacitor.
Ma'am.
Yes, Asta. Asta was asking.
Yes, ma'am.
Follow Asta.
Ma'am. Yes, like couldn't attend the class. Like, can you tell me how many pages to leave for the notes?
Sorry, I didn't understand. Yesterday you were not there.
Yes, ma'am.
Yesterday's.
I
Okay,
was asked.
yesterday's you were asking. Yesterday, can somebody else help her out with the pages number? Please, Anushka or someone who was there yesterday. I think other students were, all of you were there. Just help her with the pages that we had, so she can start writing from here. I'll send you the
Ma'am,
recording, Asta. Yes, Anushka.
Yes, ma'am.
I wrote 2 pages.
2 pages, around 2 to 3 pages leave, Asta. We had done a small portion only yesterday. The circuits having only inductor and circuits having only resistor. These topics only we did. And a numerical we had done from the first class that we had attended for that average value of. So not,
Okay.
I think leave to 2.5 pages. And do take the recording, Asta, yesterday's recording.
Yes, ma'am. Oh, ma'am.
Yes, Asta.
And there are like types of circuit and all also, no? Like C circuit, L circuit, R circuit.
See, these are those circuits: L circuit, C circuit, and R circuits. Then we'll be having in your syllabus, we have a combination of these three, that is LCR circuits. Apart from LCR circuits, you'll be having RL circuits and RC circuits. That also, these types of circuits are there. So that makes up three here, 1, 4, 5, 6 types of circuits are there in your syllabus.
So ma'am, like is this the C circuit? Because like
Yes,
the
yes.
capacitance.
Yes, yes, yes. This is the circuit having only capacitor.
Now can you just again explain? I joined a little bit.
Which part? Okay, Imal, I think you had joined late, no?
Yes, ma'am.
Okay. See, this part involves what? Your current is equal to rate of change of charge. Whatever is the charge that is present, rate of charge is equal to current. That is the formula of current. That is the definition of current. So charge is written as C E naught sine omega t. Why? Capacitance multiplied by potential CV, Q is equal to CV is there, and V is written as E naught sine omega t. V or E you can write, EMF basically. Fine, till here it's clear. Now when you differentiate sine omega t, the constant comes out. We are not integrating this time, we are differentiating it. So when you differentiate it, you get what? Omega comes out as a constant and cos omega t you get. And rest of these three terms are constant. Now see here what has been done. Till here I think you will be able to understand, because this is just trigonometric identities that have been applied. See, omega C E naught is there. If I bring this in the denominator's denominator, like if I write E naught divided by 1 by omega C, See, Imad, there won't be any difference in these two. If I
Yes.
write it like this, then I'll bring it up in the numerator. Again, it will become omega c e naught. So I'm getting this equation back.
Yes.
So do you agree with the fact that this can be written as this?
Yes, ma'am. Agree.
Agreed? So see, that's what I've written. Now see, I is equal to I naught sine omega t plus pi by 2. This becomes the resistance for this circuit, that is XC. We write this term as XC the way we had XL no, for omega L in the last circuit yesterday for inductors.
ma'am.
Similarly, this is 1 by omega C. All right.
Okay.
And rest of the
Okay.
things I think you'll be able to manage when you write it. Wherever you get stuck, let me know. I'll repeat it. All right.
Okay, ma'am. Thank you.
Ma'am, just 2 seconds. Yes, ma'am, done.
Yes, Taj, did you try this question? I think sufficient time is given for it. See, inductance is given to you as 25 millihenry. So this can be written as 25 into 10 to the power minus 3 Henry. So this is connected to a source of 220 volts. So as I've told you, this becomes what? This becomes your ERMS. Whenever nothing is mentioned, by default, you have the RMS value because you get the root mean square speed. Now, if the inductance, inductive reactance, find the inductive reactance and RMS current in the circuit if the frequency is given to you as 50 Hertz. Fine, frequency is given. So inductive reactance can be calculated as omega L. Omega is not given, so we'll write it as 2 pi nu L. So this is 2 into 3.14 into 50 into 25 into 10 to the power minus 3. This much ohms is the inductive reactance. And see what will be the IRMS current. IRMS will be simply ERMS divided by XL. So ERMS is 220 and XL, just see, solve what you're obtaining. 2 into 3.14 into 50 into 25 into 10 to the power minus 3, this much of amps. Fine. Note it down. One more question we'll do. Then we'll move on to LCR circuits. Yes, Emad, correct. It should be 28 amperes. The answer should come out to be 28 amperes. This will come around 7 point something. When you divide it, you will get it as 28 amperes. See, it says that self-inductance is given to you as 1 Henry and inductive reactance is given to you have a reactance of 3142 ohms. Fine. And you are asked to calculate the frequency. See class, XL is equal to 2 pi nu L. From here, pi is missing. Rest of the things are given to you. So this is also not difficult to calculate. This will become what? Pi nu will be equal to 3142 divided by 2 into 3.14. Let's write it as 2 so that we get a definite answer. And L. So this becomes 100 divided by 2, which will be around 50 hertz. Second part says what? What should be the capacity of a capacitance? Capacity of a capacitor which has the same reactance at that frequency. This means now XC is also 3142. Yes, the second part says XC is also 3142 ohms, this much. And it is asking you to calculate capacitance. See, now frequency you know. So XC is equal to 1 by omega C, or you can write it as 1 by 2 pi nu C. See, frequency you have calculated from this first part. Capacitance is unknown. Capacitance will be equal to 1 by 2 pi nu XC. So capacitance can be written as 1 by 2 into 3.14 into 50 into XC is 3142. This much of fat. All right, note this down. Then we'll start with LCR circuits. A question I think you have not written, no?
Ma'am, can you explain the second part again?
See, it says what should be the capacity of a capacitor. This means capacitance. See, we have that is unknown, which has the same reactance at that frequency. Same reactance means reactance of 3142 at that frequency means at this frequency. So it means in this part, frequency is this that we have called that frequency which is mentioned, or that frequency that is 50 hertz. So in this, xc will be equal to 1 by 2 pi nu c. Frequencies that we have calculated from the first part, xc, it has mentioned that it is the same reactance. So 3142 ohms. Only capacitance is unknown. So using this formula, we'll calculate capacitance. Got it? Or any other doubt you have?
Yes, ma'am. Thank you, ma'am.
Clear? Okay. Until here.
Yes, ma'am.
Start with LCR circuits. See, LCR circuits are now, if you have understood the individual circuits, all these three circuits, LCR circuits are just combination of these. Combination of L circuits, combination of R circuits, combination of C circuits. So a resistor will be there, inductor is there, and capacitance is there, and all these three are connected in series. So that's why you also call this as series LCR circuits. Note that no two or any of these, none of them are connected in parallel. It's not inductor and resistor, you can connect it in parallel and then connect capacitor in series. It's not this way. They have, all these three have to be connected in series. So again, one last revision. Resistance, in case of resistor, inductance and potential both are in the same phase. In case of series having only inductor, potential leads current by 90 degree. In series, in capacitance circuits, potential lags current by 90 degree. Voltage will be what? If current in the circuit is, let's say, I, so this becomes I into R. For potential in the L circuits, this becomes I into R. Now, what's the resistance for inductive circuits? Inductive reactance. Similarly, VC is going to be I into XC. Fine. Now, how will we write phasor and phasor diagrams? How will we write the net resistance of the circuit? Some things have to be done. because these are combinations and one has to dominate over the other. See, phasor diagram, this is the resistor one. This is the capacitor and this is the inductor. So voltage, since it is ahead of resistor, that's why I've written over here. And since voltage is lagging behind by 90 degrees, that's why I've written it over here. Now, what is the ultimate circuit depends upon the exceeding factor. See, if you have two vectors which are exactly in opposite direction, for example, this VL and VC both are exactly in the opposite direction, right? So what will be the net value of voltage if two vectors are making an angle of 180 degree? How do you write the net value of that vector? You subtract it. If two vectors are in the same direction, you add it. But if two vectors are in the opposite direction, what do? You subtract both the vectors. So same is the case here. VL, VC, you have to find out a net circuit. So whether the difference should point towards L side or the difference should go towards C side depends upon the magnitude. So one case that is possible is if VL is greater than VC, potential of the inductor is greater than potential of capacitance. This is the case. This is VL, this is VC. I am saying this is having a greater value. So net resultant of voltage will be towards the inductor side because it is having a greater magnitude. Let's say 5 volt is there, 3 volt is there. 5 minus 3 will give you 2. Direction will be towards the greater one, magnitude having towards the vector that is having the greater magnitude, right? So if VL is greater than VC, or you can say XL is greater than XC, inductive reactance is greater than capacitive reactance. Your vector, your phasor diagram, this will be for VR, but your resultant voltage will become VL minus VC, or you can write XL minus XC. So resultant will point towards this side, L side only, which you can write it as VL minus VC, or you can write XL minus XC. But if your capacitive reactance is greater than inductive reactance, or you can say voltage across capacitor is greater than voltage across inductor, or XC is greater than XL, this is C. So how will you write net voltage? You will write it as VC minus VL, or you can write it as XC minus XL. And now how will you depict the phasor? This is VR. This time, see, if two vectors are in the opposite direction, this one is having the greater one. So net resultant will be towards this only. And this side will become VL minus VC or XL minus XC. Understood this part, why we are having two cases? Now all the time we will be considering for the net resultant also, you will be having two cases always. When once your VL leads VC, other one when VC exceeds VL. This depends upon the simple magnitude that you can analyze by looking at just the magnitude of the vector before the unit that is placed. So resistance is there, VL is greater than VR, VC is greater than VR, VL is greater than VC or VC is greater than VL. That determines where will your net resultant will point towards. So this is a generalized case, but where it will point out depends upon the magnitude. If VL is greater than VC, your resultant will be VL minus VC pointing towards L. If VC is greater than VL, you will have VC minus VL or XC minus XL pointing towards C, that is capacitive. In that case, you will say it's a capacitive circuit because that has a higher weightage. And in case of inductive circuits, you call it as inductive circuits because that is now having a higher magnitude. Tell me, these 2 points are clear? Then we'll move on to resistance.
Yes, ma'am. Clear.
Clear? To all of you or to only Anushka?
Yes, ma'am.
Yes, ma'am. Clear.
Okay. Now see, regarding the resistance. So for purely resistive circuit, we use the term R, that yes, R is the resistance for this circuit. When we shifted our circuit to entirely inductive circuit, we said XL is the net resistance of this circuit. When we had XC, we had said XC is for capacitive circuit, we said XC is the net capacitance of this circuit. It means what? that resistance offered by individual circuits we know either as R, XL or XC. But if you combine all these three, then also there will be certain amount of resistance or the opposition that will be faced by the circuit. So here what you have to do, you have to find out what's the net resultant of the circuit, right? So for net resultant, we'll do what? We'll draw a triangle. That triangle will help us in calculation. Now this resultant resistance of a series LCR circuit, or the net opposition that is offered by series LCR circuit, that is known as impedance. Impedance is just a new term. Rest of the things from here, that is your resistance word, or you can say opposition word, obstruction word, all these are same. It's just that the name that has been assigned to these LCR circuits is known as impedance. And for the derivation is very small. Usually derivation for impedance is not asked in your examination, but in the exam any question can be asked, so just in case, let's be prepared for it. Otherwise the derivation is not very important, but numericals from this part is very important. Now see, in the inductive impedance triangle, see, this is just a triangle for our derivation, for our help that we have drawn, because otherwise drawing it on phasor diagram and deriving it becomes difficult. So on one side I have taken XL minus XC, or you can, now this is which case? This is when XL is greater than XC, or you can say voltage across inductor is greater than voltage across capacitor. So XL minus XC or VL minus VC, that term. Here voltage will be VR and here voltage will be the net resultant, let's say E for the whole entire circuit. Fine. Now class, this is if XL is greater than XC. Right now only I have told you XL minus XC will be the net resultant of the circuit. So this is resistance, this is impedance, this is XL minus XC. It's just a triangle for our derivation, because if I write this directly, then you will not be able to understand from where this equation has been written. So we just draw the resistor, we draw the net resultant of the inductance, and it's like triangle law. In triangle law, two adjacent sides of the triangle represent the vectors and their resultant is given by the diagonal for it. So if one of the resistors value is this triangle, another resistor, or you can say another vector is XL minus XC, then their resultant is given by the Z. So you can relate it with triangle law. If two vectors represent the adjacent sides of triangle, their resultant will be given by the third side. This also you can say, but no need to go into the details of triangle law. Just remember there's a triangle, right angle triangle we have drawn for the derivation of impedance. Now if you write this in terms of Pythagoras theorem, if you apply, perpendicular, this is hypotenuse square will be equal to base square plus perpendicular square, right? This is the perpendicular, this is the base, this is the hypotenuse. So using this triangle, we can write this equation. Just this equation was needed. Now put in the values of Ohm's law. If Ohm's law was what? V is equal to IR. So E naught will be current in the circuit I naught multiplied by R square. This will be I naught multiplied by R square. Not R square, or just leave this. E naught, let's leave it right now. Let's write first the values of these two. So this is E naught square. Now VR, we can write it as I into R, because current is I and resistance is R. So this is I naught multiplied by R. This whole square, VR can be written as I naught R, and VL minus VC. So plus VL can be written as I naught XL minus I naught XC whole square for you. Now see, from all these terms, we can take one thing common, that is I naught square. See, I naught square, I naught square, I naught square can be taken common. What is left? R square plus XL minus XC whole square is left, right? Now bring every term apart, aside from your, bring all the terms aside from current. So what will be the value of current from here? If you write the value of current, I naught square will be equal to E naught square divided by, this is R square plus XL minus XC whole square So current will be equal to what? If you write from here, I naught will be equal to E naught, and this C, since there is no square for this entire term, we can place a root sign over here for this term. So it becomes E naught divided by under root R square plus XL minus XC whole square. So what is Z? Z is the impedance. Now impedance was the resistance for this entire circuit. So if you have the resistance, or you can say I is equal to E divided by something. If I is equal to E divided by this whole entire term, R square plus XC minus XL term, means this is now doing the function of the resistor over here. So it means R square plus XL minus XC whole square under root is your impedance for this circuit. Why? Because I is equal to V by R. The way we had, no, I naught is equal to E naught divided by XL, or you can say I naught is equal to XL, E naught divided by XC. So we concluded the fact that XC and XL are the resistors. So definitely they will be performing the functions of resistance. Similarly, here also, if you see E naught, it will be I naught is equal to E naught divided by under root R square plus XL minus XC whole square. So this is the case when XL is greater than XC. Just in case if your XC is greater than XL, see what the difference will arise. The difference that will arise will be in the difference of XL and XC. Here XL was greater, so XL minus XC we wrote. Same derivation will be there. It will just be XC minus XL whole square you will obtain for this. This is XC greater than XL. Now see, as I've told you, this derivation is not asked so much in the exam, but it can be asked. Chances of numericals coming from this topic is fine. So Z is under root R square plus XC minus XL whole square. Now the effective resistance, which you said the definition of this series LCR circuit. Effective resistance of LCR circuit which opposes or impedes the flow of current through it. So whatever work a resistor was doing in a solely resistive circuit, or the work that XC inductive reactance was performing in case of purely inductive circuits, or you had XC in capacitive reactance, that the opposition work was performed by XC in case of purely capacitive circuit. Similarly, for the combination of all these three LCR circuit, you have the effective resistance which is known as the impedance. So this Z is known as impedance, whose formula is single only, under root R square plus. Now whether it's XC minus XL or XL minus XC whole square is determined by the magnitude, because we cannot have resistance as negative. That's why we are considering this so much. Otherwise this was not our concern. Negative, if it is coming negative, then it's okay. Negative aa raha hai to negative aata. We could have left it, but since resistance can never be negative, that's why we have to keep the magnitude. One last thing, then you can note it down and we can move on to the other part. See, impedance triangle from this, if I write the impedance triangle separately, this is the case when XL is greater than XC, and this is the case when XC is greater than XL. XC is greater than XL. If I write down tan phi and cos, this is the phase difference. So if you wish, you can write tan phi and cos phi from here. Cos phi is very important. This will be used a lot. Tan phi will also be used in the numerical. So tan phi, what you can write? Perpendicular divided by the base, that is XL minus XC by R. Or for the second triangle, you can write XC minus XL by R. Cos phi will be R by Z in both the cases. So remember, cos phi for all the cases, it will be R by Z only. And it's a very important term. We'll be using it in power also, numericals also it will get used. But in numericals, you can use tan phi also. Phi is the simple phase difference that we have for the circuits, right? So phase difference will remain the same. So tan phi and cos phi, you can write it from the impedance triangle only. This triangle, we have just written it. No need to see this. From here till here, tell me if you've understood something or you have any doubts till here. Is this clear? Any queries till now?
No, ma'am, no doubt.
Okay.
Asta, Ahmed, clear?
Yes, ma'am, clear.
Yes, ma'am.
Jiva, Razan, understood?
Yes, ma'am. Just the impedance, could you repeat it, ma'am?
Yes, definitely. See, impedance, just understand one thing. resistance will be there for all the circuits, right? So if you have LCR circuits, if you have a combination of these devices, then also resistance will be there. So impedance is the effective resistance for LCR circuits. LCR circuits will be having a certain value of resistance. So that resultant of the resistances that are obtained by individual circuits, we are calling that resultant or effective resistance as impedance. Now, impedance derivation, we have just plotted a triangle. From there, what we have done, we have applied Pythagoras theorem. So now we have written the values of potential I naught R whole square plus I naught XL plus minus I naught XC whole square, like this. I naught square we have taken common, so we are left with this entire term. Now, if I write I naught square, I naught's value is obtained like this. So this is what? This is like current is potential divided by resistance. It means I can conclude the fact that this entire term is the resistance, because this is exactly matching with the standardized equation of Ohm's law. So I naught is equal to E naught divided by under root R square plus XL minus XC whole square. This gives impedance. Impedance you can say, or you can even use the term resistance, but an official authorized term, we have it for the resistance of LCR circuits, which we call as impedance. Now, whether to write, see, the formula is this only, under root R square plus XL minus XC whole square, or will it be XC minus XL whole square? This is determined by the magnitude of XL and XC. That you can see in the question. If you see one is 5 ohms, other one is 1 ohm, you can easily see 5 ohm is greater than 1 ohm. That you can depict. Now this triangle, what we have done, we have just used this triangle. If we need the phase angle that you will be needing, so you have to remember these formula as well. Simple formula, R by Z, so you have to remember at any cost. Cos phi is equal to R divided by Z, because this will be used and it is same for all the circuits. But tan phi is different in the sense whether it will be XL minus XC and XC minus XL, that will be determined by the magnitude. So we have just taken the trigonometric values for tan theta. So tan theta or cos theta we have determined, because phase angle, how will we calculate for these entire circuits? For the individual circuits, we knew one is leading, other one is lacking. But for these combination of the circuits, what we could write? Understood? Is this clear now, Jiva?
Yes, ma'am. Yes, ma'am. Thank you.
Okay. Then class, start writing it down whichever point you're not able to understand, let me know. And class, this topic is important because from here you will be having a very, very, very important topic, that is resonance. And questions from resonance do come a lot in your examination. So for that, LCR circuits is very important. So write it from here. Any queries, interrupt in between. One question let's do, then we'll stop the class. So by next weekend, most of your AC will come to an end. So this is same. E naught by Z and IRMS will be ERMS by Z. Resistance will keep on changing according to the circuits. Two more types of circuits are there that we'll do on the next weekend only. Let us now see what all topics are left from AC. Resonance and Q factor is there, one important and a very big topic. Then those two circuits are there. Then you have power and energy and transformers. These are left. So by next weekend, you'll be able to complete it. And EM waves is a topic of only one class because maximum things that you have to learn by your own. Then we'll start with ray optics. Fine, so let's do this first. And C class, after AC completes, you'll be having a test. So definitely not the next weekend, but the weekend after it, we'll be having a test of AC. So please be prepared with this. Start preparing. You have a lot of time. 2 weeks will be there. 1 week tak to yahi chalega. Uske baad that will start. Fine. So it says determine the impedance of a series LCR circuit if reactance of C and L are given and R is mentioned. R is given as 40 ohms. XC is given as 250 ohms. XL is given as 220 ohms. So which formula should I use? Which is greater, XC minus XL should I use or XL minus XC?
XC minus XL.
XC minus XL, yes, Asta. XC is greater than XL, so now we'll use XC minus XL. So RZ will become equal to under root R square plus XC minus XL whole square. See, XC minus XL is what? XC minus XL is 30. So 40 square plus 30 square, this will give you 50 ohms. Fine, easy question. Quickly note it down. One last numerical we do on this. Now just note this down. This we'll leave. This question is based on resonance that we'll do in the next class. Note down this first. And text me done in the chat column once you have completed this. Anushka, Imad have completed. What about others? Let me know once you have done.
Yes, ma'am, done.
Okay, then class resonance part and the other things we'll complete on next Saturday only. As I've told you, next Saturday, Sunday, we'll complete with this lesson, this chapter AC, and do complete the assignments that will be assigned to you. Next weekend, we'll complete with these this only single chapter, and EMVs I think we'll be able to do in the next class only, on next to next weekend. So next to next weekend, let me tell you the date.